Swayam Prabha. Digital India. Educated India.
Welcome to third lecture on video course of Tribology. Topic of this lecture is friction. Very interesting. We experience friction in day-to-day life. When we walk, we experience friction. When we cycle, we experience friction. When we drive, we experience friction. So it's a very common mode which we experience every day. And often when we go to mall, we find this kind of signal or warning that slippery when wet, or the floor is wet. So, you need to be careful when you walk. Reason being, the water plays as a lubricant layer and it reduces the friction. So, we need to walk with more force. So, the overall friction force turned out to be same. I have gone through number of books and found number of variation in coefficient of friction. So, I am just showing on the first slide of this course that typical value of coefficient of friction, which is often quoted in books. We say these values are static coefficient of friction, or these values belong to static coefficient of friction. There is some difference. Static coefficient of friction and kinematic coefficient of friction, will come to that topic later, but see what is mentioned in this table. It says aluminum versus aluminum. When aluminum rubs over aluminum under pressure or force having relative velocity, it shows a coefficient of friction 1.5. Amazing. We normally believe that coefficient of friction will not go beyond 1.0. And here we are showing the coefficient of friction as a 1.5. Similarly, when copper rubs over copper, it gives a coefficient of friction 1.5. Interestingly, this value cannot be repeated again and again. This is just a mean value. There will be some variation in coefficient of friction. Now, let us see another example. When copper is oxidized, that means when we are allowing it to contaminate, coefficient of friction decreases 2.5, so 1/3. That is an amazing thing. Coming to coefficient of friction, very high value is a gold over gold, very soft material, coefficient of friction is 2.5. Coming to platinum, platinum over platinum, coefficient of friction is 3. Well, we have two examples of the steel also. See, mild steel over mild steel shows a coefficient of friction 0.8, while tool steel over tool steel gives a coefficient of friction 0.4. That means, same material, same composition, by and large some change in hardness gives a variation in coefficient of friction. So, it is not only the material property, it is a property of a system. Coefficient of friction will vary if you change any one parameter of system. You change temperature, coefficient of friction will vary. You change material composition, coefficient of friction vary. If you change the surface roughness, it will vary. If you change hardness, it will vary. So, we can say observation from these slides are mu, the coefficient of friction, is greater than 1.0. Mild steel versus tool steel shows different coefficient of friction. Now, you say that mild steel or wild steel shows coefficient of friction 0.8, tool steel versus tool steel shows coefficient of friction 0.4. If I do intermediate, it will be somewhere in between, like mild steel versus tool steel will be somewhere 0.6, something like that. And another interesting thing which we observed is that when copper is getting oxidized, coefficient of friction reduces to 1/3. That means, mu depends on the environment. Let us take another example or other published data. Here the coefficient of friction is given to us and it shows that steel is getting rubbed on indium, steel or lead brass, steel on bronze, steel in brass, cast iron, aluminum bronze, so on, and finally comes a steel on a steel. That means similar kind of material will give high coefficient of friction compared to two different pair of materials. I will say the tribopure made of two different material will show lesser coefficient of friction compared to tribopure made of the same material. And another interesting thing we can observe from here in this this data is that when there is a thin lubrication, partial lubrication, some sort of lubrication is provided at the interface between the two materials, then coefficient of friction reduces by 1/10. And if we can completely separate two surfaces, no asperity contact, that is why we are saying is a hydrodynamic lubrication, thin thick film lubrication, then coefficient of friction reduces to 100. That means 1% of coefficient of friction which we can experience in dry condition. So, here it is indicated that lubrication is very, very important to reduce the coefficient of friction, to reduce energy loss. However, when we are talking about the reduction of coefficient of friction, I believe there are a couple of examples where we regularly require coefficient of friction, a high coefficient of friction or high frictional force. I given one example initially that when we walk, we require some coefficient of friction at our shoes level, or we said that we require coefficient of friction at between shoe and the road. So, there is a need. If we are providing a lubricant layer there, the coefficient of friction reduces and our efforts towards walking are increasing. So, that way we can say friction is important. We have another example also, like a brake. When we want to stop automobile, we apply a brake. The coefficient of friction works, where we are trying to enhance or increase the coefficient of friction. So, it is not only that we always target lesser coefficient of friction, we can target high coefficient of friction also. So, in tribology we can say that we work more towards the controlling friction compared to talking the lesser friction or higher friction. We want to make coefficient of friction at a desirable level, and maybe 90% cases we try to reduce coefficient of friction. Is almost all a machine wherever there is a interface and friction is experienced and that requires power or energy loss, we want to reduce it, because energy loss will enhance the temperature, will increase the temperature, and we do not want that. So, by and large we want to reduce, but we have examples where we coefficient of friction also can be increased, we want to increase it. So, in short we can say tribology means controlling friction. What are the observation from this slide? Say that under dry lubrication condition, mu ranges between 0.1 to 1.0 by and large, except the few example like a nickel on nickel, gold on gold, platinum on platinum, copper on copper, so on. Again, this will not be repetitive results, these are the mean values. Maybe one lab it has been experienced, this kind of coefficient of friction have been experienced in one lab, but if you do similar experiment in other lab, other environment, there is a possibility of change in coefficient of friction. And another observation from this slide is that very thin lubrication reduces coefficient of friction by 10 times. You invest delta money and you get 10 times profit. That is encouraging to learn the tribology. Here is another chemical related chart with us, which shows that we should choose proper material pair for tribological application. Let us take an example. We are saying the lead can be selected with the chromium, lead can be selected with the cobalt, lead can be selected with the nickel, lead can be selected with the iron, and lead can be selected with the neodymium. Why we are saying this to be selected? Because this circle is filled, it is a black circle, and this table indicates a fully occupied or the complete black circle means a low adhesion force. If the adhesion force is very high, adhesion will increase the friction force. So, if you want to really target for a low coefficient of friction, we choose that kind of material pair. Similarly, we can choose a silver versus chromium, silver versus cobalt, provided we have enough money, because silver is one of the costlier material compared to lead. So, that is why we in most of the application we use a lead compared to silver. In this, from this table also we can see that aluminum should not be used against tungsten, aluminum should not be used against the chromium, aluminum should not be used against the nickel. So, there are some restrictions. Partly it can be used with zirconium and cobalt, but if we treat this nickel, metal properties will change, surface properties will change, and we can utilize against some other material pair, right. So, this is just a guideline for us, but it is not a formula. If I have a cheap material like aluminum is available in abundance, we can use that material with modification to reduce coefficient of friction as per our desire. So, we can say that the observation from this slide is similar materials have high tendency of adhesion. I skip that. This is in this case particularly, wherever materials in this case zirconium versus zirconium, we have left empty circle, empty place. That is always known, zirconium versus zirconium will have a more and more molecular attraction. We say the similar material have more attractive force, and then they will try to increase adhesion force, or we say that they have a cohesion force, and cohesion force will be by and large more than adhesion force. So, that should be avoided. Now, initially or maybe first or second slide I mentioned about the static and kinetic coefficient of friction. We are going to explore that. What is really static and kinetic coefficient of friction? To explain that, let us take this figure. You say first point, we are applying 20 Newton load to move this block, 100 Newton block. 20 Newton load is applied on 100 Newton block, which has a coefficient of friction 0.5, and we find that block is at same place, we are not able to move this block. Now, if we increase this force to 40 Newton, apply some additional load on that, still the block remains the same position, it does not move. Reason being, opposing force, friction force is higher than applied force. However, when we apply 50 Newton load, there is a possibility of sliding of block, if coefficient of friction which is estimated is accurate. In that case, block will start sliding. As it gets momentum, then opposing force or friction force reduces, and this is reduced to the 40 Newton. That means, we get some sort of movement, some sort of acceleration on this block, and after that this friction force is steady. It remains the same 40 level or 40 Newton level. In other words, friction force starts from a 0, increases to the value mu into whatever the normal force. After that, there is a possibility of decrease in that magnitude, and what we say, this is this points belong to the static friction force, and this line belongs to the kinetic friction force. Kinetic friction force in this case is shown to be lesser than static friction force, but it is not always the case. Most of the times of metals it is, but for polymers it has shown a different behavior variation in that. Now, this table is shown to indicate that there is a huge variation in static and kinetic coefficient of friction. Mu s here represents the static coefficient of friction, and mu k is the kinetic coefficient of friction. So, this literature this table has been picked up from one of the book. Say that here the wood on wood coefficient of friction varies from 0.25 to 0.5, almost 50% variation, and kinetic coefficient of friction which is having steady value, that is a 0.19, which is much lower than 0.5, or we say intermediate value 0.4 is almost half of that. However, in other case wood on wood with a lady given as a dry condition, again coefficient of friction was this, but kinetic coefficient of friction was higher in a different lecture. That means, first data is from one literature, second data is from other literature, almost similar kind of wood material have been used. In third case, say wood on wood, coefficient of friction is varying from 0.3 to 0.7. Similarly, we have number of examples. We say that just slight change in their fiber orientation, coefficient of friction is varying. An interesting thing is that kinetic coefficient of friction is shown always, in this case, always a lesser than static coefficient of friction. Is there any problem? If there is a difference in a static coefficient of friction and kinetic coefficient of friction, will there be any problem? Yes, there is a problem. We say in hydrodynamic bearing, when we start rotation of the shaft, coefficient of friction may be around 0.3, and after development of hydrodynamic film, coefficient of friction may reduce to 0.01 or 0.001. There is huge difference. If I want to run the shaft for longer duration, I had to keep some power source to start the shaft. That requires high friction force, or that requires to overcome high friction force. While for running condition, I do not require that much power. So, there is a problem. Unnecessarily, initially we have to spend too much money on the power source if coefficient of friction is higher. If it is on same level, whatever running coefficient of friction is there, then we will be requiring the same power source. We do not have to put additional equipment in a machine. So, by and large we should aim to keep same coefficient of friction throughout, maybe the start to end. That will help us. There is another problem. I talked about the power source of this in this case, but there is another problem also, what we call as a stick slip phenomenon. Let us say we want to run some one component or the other component at the micro motion device, maybe like we want only very low velocity. What will happen in that case? We supply high force, it starts sliding, it will come down. Because of the very low velocity motion, it will again come to the stationary, again we have to push it. That means, we need to shuffle high force to low force, high force to low force, and that will be a stick slip phenomena, which is often experienced in the micro machine devices. It is an important topic, and it induces a vibration, which we will be dealing in friction topic maybe in a 4th or 5th lecture. So, what are the observation overall? We say the coefficient of friction is greater than 1.0, which is generally not written in number of books. Then we say the mu depends on environment, which does not come in ordinary friction loss. It depends on the hardness also. It depends on chemical composition. So, coefficient of friction from one lab to other lab can vary easily because of these reasons. Then we can say third point is very thin and thick lubrications reduce mu, the coefficient of friction, by 10 to 100 times respectively. That means, if you are providing thick lubrication, there is always reduction in friction, but controllability will reduce. So, if we want more and more controllability, naturally we have to compromise between thin and thick lubrication or 0 to thin lubrication. Another interesting point which we observe is that tribopure, which having a similar materials, have a high tendency to show have a high tendency of coefficient of friction, or should be avoided as far as possible. Interesting thing is that when we use a ball bearing example, we use in both the cases the same chromium steel say 52-100 SI grade. Reason being that we are keeping very high hardness, where the plastic deformation or any additional friction devices can't take place. That means, we make component in such a manner, or make surface of the material in such a manner, chemical composition is not going to play much role. In that case, we can use a similar material, similar hardness, but otherwise for common application we should avoid similar material pair. And last point which is written here, that difference between the mu or static coefficient of friction and kinematic coefficient of friction may induce friction instability, which will be covered in subsequent lectures. But all these were shown as only data, no science was explained as such, no quantification was given to, no explanation in mathematical term was given to us. We have understood, we have not explained that. So, there is a need to understand science behind this friction. Let us start. Say that we can start with the dry friction. We are assuming this third substance is not available, the lubricant is not available. It is a dry friction. We say the fluid in form of liquid, in form of the powder or in form of gas is not available over here. And there is a possibility of aspirative contacts coming and interfering motion of other components. And there is a possibility of loss of wear, loss of material means wear. There will be some effect of surrounding medium, there will be surface deterioration, and that is why there will be a generation of particle, generation of debris. Now, to give a complete view, let us start with history, how friction was evolved or how friction was expressed in some of the laws which are generally given in common textbooks. We say that Leonardo da Vinci was the first person who did extensive experiments, and based on his experiments he could conclude some results. What were those results? He said that friction made of same weight, that means he was emphasizing on the weight, will be of equal resistance at the beginning of movement. That means, if there is a some weight W, friction force will be decided based on that. Whatever the area you choose, you choose 10 by 10 or you choose 5 by 20, any multiplication which gives the same area, or maybe any weight, any dimension which gives the same weight, that will give us same friction force. That was interpretation by da Vinci. And second interpretation what he mentioned is that if I double the weight, friction force will double. That means, first law can say the friction force does not depend on area of contact. Second, friction force depends on applied load or weight of the component. These laws were rediscovered by Amundsen, and he proposed a few laws in 1699. First, he also showed that friction force does not depend on area of contact. However, he changed the second law. He said friction force is proportional to normal weight or normal force. He removed the word weight or applied force directly. He said that we use the word normal. It has to be normal, then only we can say friction force is proportional to that. He gave some examples, something like this. Let us see if there is a one block, other block and third block. In first block, weight is towards the gravity downward direction. So, here normal force will be mg. If I push this block in horizontal direction, naturally friction force, which will be a maximum resistance force, will be equivalent to mg. Now, if I apply our pushing force is at some angle theta, what will happen in that case? There will be one component coming vertically down and other component will be going horizontal, and friction force will be based only on a horizontal component. What is the drawback on his side? You say that whatever the weight was there, in addition to that, friction force is this tangential force is creating a component to resist. That means, this f sin theta is additional component, it is increasing the friction force. In third case, it is subtracting, we are trying to pull up, where the one component is vertical, which is acting against the gravity force. That means, it is helping us, and friction force will be reduced in this case. So, what we say, the da Vinci's law, the friction force is proportional to the weight is not the real case, and Amundsen has modified. He said that friction force should be stated as proportional to normal force. It is not directly proportional to weight. Now, how we are applying or how we are pushing that block or pulling that block, that is going to decide what will be the friction force, and that is really the case, and that is why it has been again and again repeated in a number of books. Another interesting thing from Amundsen was that he did a number of experiments, and by and large he found that coefficient of friction is equal to 0.3 for most of the materials. That means, if I do not have any knowledge any time, or maybe say I am doing design at the start and I have not selected material pair, or I am going to select the material pair based on the strength criteria or the stiffness criteria, that will come much later. In that case, I can choose a coefficient of friction under drag condition equal to 0.3 at the start. So, these results were encouraging, and we account these results. Later, Coulomb proposed few additional points in 1781, where first thing, first more important thing is that he could identify there is a difference between static friction force and kinetic friction force. That was one of the best achievement, a very good achievement from the Coulomb. Another thing, he came with micro models. He said that aspirative contact will happen. That means, there is a discrete point contacts when there are two materials coming into contact. Before that, nobody else could point it out that there is a discrete point contacts, and that because of this there will be some interlocking, and he mentioned that friction force will be induced because of interlocking. He gave couple of examples, something like that. There is a roughness profile of one surface, roughness profile of other surface is more like a sawtooth profile. When the normal load is applied and friction force is trying to push it up, what he thought, Coulomb thought that maybe without any deformation it starts gliding up, as it requires a force to move component out of pit, that is a friction force. However, later it was realized that when it is going down, same energy will be gained back. So, there should not be any friction force. Some explanation was given that there is always a hysteresis losses. Material when is moved from one place to other places, not necessarily we will get 100% energy back. Some energy will be lost, and that is going to give us coefficient of friction, or that is going to give us a friction loss. Coulomb also mentioned that friction force does not depend on area of contact, and another interesting point which was pointed out to Coulomb, the whether coefficient of friction will depend on velocity, relative velocity, because this model was given by him. It's clearly when you are pushing over the rough surface, it takes slightly more time from a stationary position, but in running condition, naturally this component will not fall back to the complete depth. It will be at the partial level. That is why the kinetic coefficient of friction was lesser, what was suggested by Coulomb. But this depends also on velocity. If we say that speed of velocity of this component, you push hard and hard, coefficient of friction should be reduced. But Coulomb did some experiment, and based on that he concluded coefficient of friction does not depend on velocity. It is only initial velocity, static coefficient of friction, and once it starts sliding, start moving, then there will be only one kinetic coefficient of friction. It is not going to continuously reduce with the velocity. Then an interesting thing came in 1929, as Tomlinson gave a theory related to molecular attraction. He said that when one component or one element is capped on other element, then there is a possibility of molecular attraction. We know atomic forces, we know that some material have a more tendency to attract compared to the other materials. Take an example of ceramic, they will be having lesser tendency for the molecular attraction, but for metals they will be having high tendency to attract other material. So, based on his experiment, he did an extensive experiment and then came up with some curve fit equations. What are those curve fit equations? Is something like the F is the friction force is equal to 1.07 theta 1 theta 2, where theta can be given for individual material, and he also thought that two materials in one tribo pair are playing a role. Theta 1 is this theta for surface 1, this theta for surface 2, and he mentioned that this depends on material properties. It depends on E and G, Young's modulus and shear modulus. If there is a high shear modulus, the theta will be lesser, coefficient of friction will be lesser. Indirectly mentioned that the material which have a high strength, that will have a lesser coefficient of friction, and it was also known that for softer material will show a higher coefficient of friction, because deformation will be more, energy loss will be more, coefficient of friction will be more. For harder material, deformation will be lesser, and that is why the coefficient of friction will be lesser. So, this theory was justified to some extent, and just to get a flavor of this theory, I took 3 materials, the clean steel, aluminum and titanium, and these formulas were based on unit in MPP, mega PSI, and that is why we are sticking to the same unit, we are not changing to SI units in this case. Let us take a clean steel versus titanium. If I use formula, if I substitute 30 12 in theta 1 to find out theta 1. Similarly, if I substitute 15.5 and 6.5 in this theta value to find out the theta 2, I will be able to get out theta 1 and theta 2, substitute this value, I will be able to find out friction force, and that turned out to be 0.5039, roughly 0.5 coefficient of friction, that is again static coefficient of friction. If I use other material, say the clean steel and aluminum, now here the coefficient of friction is increasing, that is this is the experimentally observed results. So, here reason being that G is reduced from 6.5, it is coming to 3.6, from 15.5 E is coming to the 10. Naturally, E and G are reduced, that is going to give us a higher coefficient of friction. Take a third example, where we say the aluminum versus titanium. Here these are 2 weak material, those 2 soft material, and coefficient of friction turn out to be 0.7. These were experimentally observed results, and to some extent this curve fit equation are valid, but it does not give complete science. It gives the results based on experimental results. It is only empirical relation. Still the science is required to explain this. And as I mentioned that metal have a high molecular attraction, so they will show high coefficient of friction. Ceramic will be having a lesser molecular attraction, so they will show lesser coefficient of friction. Polymers will also show lesser coefficient of friction, because they have a lesser tendency to attract molecularly or experience molecular force. Now, we want to start with a scientific explanation of a dry friction. We believe there are 2 modes of friction, or 2 sources of friction. One is called the adhesion, molecular attraction, other one is called a deformation, one surface is trying to deform other surface. So, that there are 2 friction sources, one is adhesion over here, deformation this one, and resultant friction will be a summation of, it will be more like a superposition. Friction force contributed due to the adhesion and friction force contributed due to deformation, it will be just summation of these 2. Now, just to make a variation, if I want to lubricate this type of surface, what will happen? Lubricant is going to reduce adhesion, reduce molecular attraction between components, between tribopair. If it is a reducing molecular attraction, naturally adhesive force will be negligible. That means, only there will be one source of friction, that is deformation. Now, if I come to the other end, we say we want to make extra smooth surface, no aspirate at all, almost perfectly smooth the surface of mica or mica, then what will happen? There will be negligible deformation, there will be only and only adhesion force, right. So, there are 2 extremes, we can lubricate surface partially, or we say that mixed lubrication case, where the adhesion force turn out to be 0 or negligible, and when we use an extra smooth surface, then we will have only adhesive force and the deformation force will be negligible. We will try to explore both the options and develop individual expressions one for adhesive force, other will be for deformation force. Just before developing some expression or mathematical relation, let us see the example of this carbon graphite steel versus stainless steel. This carbon graphite steel is having some attractions towards aluminum. That is a strange thing, because this is made of the powder form, and when it is rubbed, what will happen? It will leave its prints on the shaft. That means, one layer will be transferred. So, this surface is transferring this carbon layer, graphite layer on the surface. So, it is interesting thing, people have experience that adhesion to some extent can play as a good lubricant role. What is happening in this case? We are utilizing adhesion after understanding. We are transferring a carbon graphite layer on the other surface, and that carbon graphite surface will subsequently act as a lubricant. It will be more like a powder lubrication. So, it is important, or it has come after understanding how adhesion can be utilized to the better side. Let us take another example. Is a steel pin is pushed in some block of indium. When you push it, what will happen? There is a possibility the indium is soft material, steel will penetrate in that material to some depth. And if I push it back, or we say the lift this rod back or pin back, we will find some material attached to this rod. You can see there are some particles attached to this rod, and that is a material transfer. Indium is transferring the material. Now, this is good to know. When we are pushing it, indium is having some attraction towards a steel surface. It gets deposited on a steel surface. When we are removing it, it is not getting fractured at the interface, or we say that interface between steel and indium is stronger than indium itself, or in other words, indium has a lesser strength compared to the strength of interface made by steel and indium. Right. So, when we understand this, we can say that we should design interfaces in such a manner, interface need to have a lower strength compared to any of material, whether it is a material 2 or material 1, or whether steel or indium. If I provide a lubricant the interface, that will have some strength, and that strength need to be lower than indium material, then only we will be getting clean surface, we will not get any material transferred in that case. Now, let us develop a theory where we are saying that when you are applying applying a force on one irregular surface against other irregular surface, they are going to undergo maybe say under plastic deformation, and due to that plastic deformation there is a possibility of cold junction formation. This is a cold welding or cold junction formation, which is a cold welding under pressure. You are applying a force, and that is why this kind of welding is happening. Now, if I apply tangential force, I push, or we say the push this component to the right side, those junction will be sheared. Now, depends on how this components or this interfaces are sheared. If interface is sheared, then there is no problem, but if the interface is getting a higher strength compared to the one of the material, then there is a problem. That means, higher coefficient of friction will be there in that case, right. Now, if we develop mathematical relation, we can say simply that we know what is the hardness of a softer material. If I am using this as a material 1, is a material 2, and material 2 is a softer material, it has some hardness H. If I know that H, if I know W, normal load which is being applied on this component, then I can find out what will be the area of contact, right, because here the plastic deformation is considered. That is why the hardness is accounted. If we consider only elastic deformation, then I can think about the yield strength or proportional limits, but we are considering the plastic deformation, that is why hardness is accounted in this case. So, area of contact, which is the real area of contact, can be figured out by using this relation W divided by H, and this area need to be sheared. whatever the junction was made, that need to be sheared. So, to shear this we need to apply some force in tangential direction, and I can represent this as a F addition. F addition can be given as a area or real area of contact where this kind of bonds are made into the shear strength of junction. May be variable, may be constant, we can take a mean value of that. So, if I know the friction force, if I know the normal load, I can find out the coefficient of friction. That will be simple relation, mu A is equal to F A divided by W. Substitute value, we say that A into S into A, and here it will be A into H. A will be cancelled out, that means we really do not have to find out what is the real area of contact, which is a very difficult parameter estimating theoretically. We can find out experimentally, but estimation using theory is slightly difficult. So, in this case we are not getting area of contact at all, we are getting S divided by H, and both are the material and surface properties, and both belong to same material, both belong to the softer material in this case. Only point variation will be that quite possible S for the softer material is higher and interface has a lesser, in that case S will be slightly lesser. However, for time being we are assuming S is a material property of softer material, H is a hardness of softer material. What is interesting in observation from this? Say that shear has strength and hardness related to material. That means, if I choose a one material, if I choose the indium, now choose any other material pair which has a high shear strength and a higher hardness, I should get same coefficient of friction, because indium is going to decide what will be the coefficient of friction. Now, if I choose a steel, if I choose a chromium, I choose a nickel, I choose any other material, indium may be one of the soft material, it should show the same coefficient of friction with any material pair, which is not the case. That means something else is required to explain that phenomena. This is not complete. It needs some additional theories to explain it. This is what I mentioned over here. For most of the materials, if I assume this is not happening, now we will come to the other arguments. We say that for most of the material, hardness can be given as a 3 times of the Young's 3 times of the yield strength, and shear strength can be given as a yield strength divided by root 3, that is von Mises stress theory. Here I am trying to utilize solid mechanics to interpret what will be the coefficient of friction if I want to use based on addition theory. If I substitute this S is equal to sigma divided by root 3 and H is equal to 3 sigma, what I will be getting roughly this coefficient of friction equal to 0.2. That means, whatever the material pair I choose, coefficient of friction should be 0.2. It does not depend on the material pair. That means, this theory is insufficient to explain what is coefficient of friction and how coefficient of friction will vary with material properties, right. And this is what we showed initially, this table. So, that coefficient of friction will be different. It depends on the material pair. If the material pair is same, then coefficient of friction will be high, which is not the case in this. It says that one of the material has a shear strength, which is softer material, which is shear strength is accounted, and hardness of softer material is accounted. So, this theory is insufficient or unable to estimate different value of mu, coefficient of friction, and there is a possibility that theory of deformation, obviously the other source, friction source, may give some good results, as we are not happy with the results obtained by this addition theory. So, let us explore what is what deformation theory says. The deformation, we can assume different kind of asperities, because the deformation surface roughness is playing important role in deformation. Let us take first example is a conical asperity, and we are assuming same cone radius for all asperities. There may be n asperities on a desirable or a surface area which we are defining. It is trying to it has pushed This conical cavity is at some depth in a soft material, the depth is h, and we are trying to push this asperity so that sliding occurs, right. In that case, what we can say, the expression can be given, or we need to find out what is the area, projected area on which the load is applied, and what is the area on which the force is, tangential force is applied. Then we can calculate what will be the friction force, what will be the normal force, and based on that we can find a coefficient of friction. So, for doing that, let us start with the area. We say that this is a conical area, and we had to find out only this much, because even though cone has a higher projection or the dimensions are more than this, but contact is happening at this radius only, right. So, area pi r square is the area plus half, because the 0 over here is the average area, and n is the number of asperities. So, total area of contact can be estimated. I am not saying that this is accurate, it is estimated roughly n into 0.5 into pi r square, and r is a cone radius. Now, we know the area of the contact. If I multiply with the hardness, I will be able to find out what is W, what is the normal force applied on this asperities. All asperities are a complete area which has n asperities in contact. To find out the friction force, we need to find out the projected area on the other side. That means, I want to project this cone on normal plane perpendicular to that. You say that tilt this figure by 90 degree, so that line appears in the slide, and that will give me area of contact. Okay. So, this is having a 2 r as a dimension perpendicular, and the depth we know is the h. So, half of the area will be counted, because half surface it will be r into h. So, friction force can be given as n number of asperities into radius of the cone into h the depth in soft material into hardness. Now, if I take an expression mu, I assume the mu is equal to F by W, that means friction force divided by W, and R h into capital H divided by n into 0.5 into pi r square into h, right. So, what will happen? Some terms will be cancelled out, and we know expression of the cot theta will come, that this theta is known. We know this depth, we know r, we can find out cot in terms of h and r. So, coefficient of friction can be expressed as 2 divided by pi. So, pi is roughly 3 point something. So, it will be 0.5 and into cot theta. Based on cone angle, based on this theta angle, we can find out what will be coefficient of friction. I did some calculation, and given the in tabular form, you say when theta is phi, that means the asperity is very sharp. Asperity is very sharp. In that case, what will happen? It will penetrate immediately. It is more like a needle, it will penetrate it immediately. However, if the theta is increased to the 85 degree, is almost a flat surface, then coefficient of friction reduces to very low value, almost negligible, say 0.055. However, intermediate value maybe 80, 70, 60, some coefficient of friction is given. But one interesting point to observe from is that there is a highly sensitivity. This expression are very sensitive towards the theta. Just changing by few degree, coefficient of friction is changing drastically. Take an example from 5 and 10. If theta is only 5 degrees, a half cone angle, overall cone angle is 10 degree, and here from 5 to 10, that means overall cone angle is 20 degree. From 10 to 20 cone angle, what we have find coefficient of friction of 0.73 and here 3.6, almost half. That means, this by expression is very sensitive towards the theta, and getting any reliable theta will be difficult for us. However, experience says that most of the time after initial running in time or running in period, this theta turn out to be greater than 80 degree by and large. The coefficient of friction will turn out to be 0.1 or say 0.01 in this case. So, if I add coefficient of friction due to adhesion, coefficient of friction due to deformation, I should not get coefficient of friction more than 0.3. However, in the first slide which I showed experimental result, coefficient of friction was estimated also as equal to 3.0, very high coefficient of friction is 10 times compared to what we are able to predict through theory. Interesting thing is that when we are saying this cone, when it is coming almost to the flat level, or theta is on a higher side 80 degree, do I need to use this conical theory? Instead of that, I will prefer to use asperity as a spherical shape. As a cone, particularly in this case shown, the cone angle is increasing, it will turn out to be more and more uniform, or a flat surface, a theta is 90 degree, but lesser than that it will be some sort of some sort of a spherical shape with some round edges, generally happens during the process. So, let us explore what is what kind of expression I can get when I assume there is a spherical asperity. In this case, we are saying that this is the hard material having a spherical asperity, and radius of a sphere is given as a r. It has penetrated to some depth, that the depth is h in a surface. When I project on as a top view of this contact, what I find some radius d, some radius d by 2, and depth will also be d in this case, because this is a whatever the cross section I take, that will be circle, right. So, whatever I get over here, the d by 2, same radius here I will be getting d by 2. However, if I project in perpendicular direction, again the depth will be h, and other dimension will be d. So, using this dimension, I can find out what will be the area of contact, I can find out the normal force, and I can find out tangential force. So, area of contact will be pi r square, in this case r is 0.5 d, half of the area in a projected direction, or the half which is getting pushing asperities towards a soft material, and when we express in terms of d, it turn out to be n pi d square divided by 8. That is the expression. So, if I multiply with the hardness, what I will get? I will get a normal load as a number of asperities, contact area due to one asperity into hardness. What I will be getting F, friction force. It will be the tangential, as I say that if I move vertically by 90 degree as in the side view, I will be getting depth h, and d will be the other dimension. So, in that case area of contact in tangential direction will turn out to be, with some simplification, 2 h d divided by 3. We do not know the dimension d. So, we can express d if express d in terms of capital R, or express h in terms of capital R, the radius of this sphere, then we can get a good results. However, in this case we will try to express h d in terms of capital R. So, we can play with h by r and find out what will be the result and how the results will vary. So, in that case, if I want to find out the coefficient of friction due to the deformation, particularly due to spherical asperities, I can simply say f divided by h, expression will be something like this. Rearrange this, expression will turn out to be 16 divided by 3 into pi h by d. Here d can be given with assumption that h is very low compared to capital R, that when depth of penetration is much lower compared to the spherical radius, or with the radius of the spherical asperity. In that case, I can give expression as 8 into h into r, that means this overall expression can be given in terms of h, depth of penetration, divided by radius of sphere. Now, with this expression I can play, and then I can find out what the result, what results I can get if I change h in terms of percentage, with a 1%, 2%, 3%, 4%, 10%. Well, I am going to get a very high or different results. So, I did that is we are taking example as a h divided by r in a percentage, assuming depth of penetration will not be significant. That means, I can go maximum to 10 value. Beyond that, this expression will not be valid. We have to change the expression if we are going beyond that. Now, coefficient of friction is not very sensitive as what was shown in conical cavity, conical asperities. So, from that point of view, we feel that this expression is slightly better. It's not very sensitive and it may give very good results. And so, here the coefficient of friction when H is almost negligible, depth of penetration is almost negligible, is almost 1%, coefficient of friction can now be 0.06. As we are increasing depth of penetration, coefficient of friction is increasing, but maximum value is turning out to be 0.2. That means coefficient of friction is not very high in this case. So, even in this case, if I add, or we say that few asperities are conical, few asperities are spherical, so I will get some intermediate value. And but after running in time, all conical asperities will be damaged, will be turn out to be some sort of spherical asperities, and I may get a result somewhere intermediate results. But that still is not going to give us satisfactory results which we obtained earlier, or we showed an as an experimental result the coefficient of friction very high, say 1, 2 and 3. That is not been explained with these theories. That means, these theories have some shortcoming. These are classical theories. We need to explore some new theory. We will try to explore that theory in our next lecture, which will be mostly on the friction due to junction growth, where the Mohr cycle stress relation will be shown, and so that we can find out reasonably good expression to estimate coefficient of friction. With this, thank you. Thanks for your attention.